Welcome to our second lecture on acid-base equilibrium. Again, remind yourself we're talking about proton transfer. Acids have a proton, H+, they will transfer it to a base. We want to look today in this video at weak acids and weak bases. Let's consider again what we talked about before. A strong acid is one that completely dissociates. So however much acid we start with, we end up with that much hydronium in solution. Weak acids, however, can be thought of as establishing an equilibrium. Here we have a simple equilibrium for a weak acid, where we're representing our acid as HA. It donates a proton to water to form hydronium, and what's left is this conjugate base that we were talking about in the last video. The equilibrium constant for this reaction we're going to label as a Ka. A just stands simply for acid, so it's going to be our products, hydronium times the conjugate base divided by the concentration of the acid. For weak acids, these Kas are going to be less than 1, and in most cases very much less than 1. So there's only a partial or a slight dissociation. Let's remind ourselves again, the larger that equilibrium constant, the stronger the acid, the more products we get. The Ka for most weak acids are going to be less than or equal to 10 to the minus 4th, and we'll recognize weak acids formulaically by the fact that they will either begin with an H or they'll end in CO2H, but they will not be one of our strong six. Here are some examples. HF, hydrofluoric, HCN, hydrocyanic, H2S, hydrosulfuric, be careful here, HNO2, that's nitrous acid, and then here are three examples of those acids that end in CO2H. We call these are organic or carboxylic acids. Those are carboxylic acids, carbon, oxygen, and then the acid. These are respectively formic acid, that's what an ant bites under your skin. This is acetic acid, or the acid component of vinegar. And this is benzoic acid, which conjugate base, the benzoate ion, is a common preservative, and you'd find that in your carbonated beverages that you drink. Now, when we're dealing with weak acids, we're going to use a rice table to do our calculations to determine our pH, or to use the pH to determine the concentration of our acid. Let's look at an example here. Here again is a weak acid in general. It says here, let's calculate the equilibrium hydronium concentration in a solution that's initially 0.85 molar in acetic acid. And we're told that the Ka for acetic acid is 1.78 times 10 to the minus 5th. So to approach this, we're going to set up our rice table. Now, the formula for acetic acid is CH3CO2H, but we can represent it generically as simply HA. What we're concerned with here is that this is an acid, so that it has a proton that it can donate. So generically, here we go. We've got HA plus H2O is in equilibrium with hydronium and A minus, the conjugate base. So here's my acid, CH3OH, there's water. The water accepts a proton, become hydronium, and the acetic acid loses a proton. Look, it's missing that H and it's missing a plus because it's got a negative charge, and we get the acetate ion. So here we are again. So here's our rice table again, and now we're going to put the initial concentrations in. Again, we're told that the acetic acid is 0.85, so we put that in here. We don't have any conjugate base before the reaction begins. The equilibrium is established. And here I've said that the hydronium ion is essentially 0. What we're going to find, and we talked a little bit briefly in the other video, is that water auto-ionizes, and we get a very small amount, about 10 to the minus 7th, of hydronium, even in neutral water. So it's not exactly 0, but it's very, very close. Now let's calculate our change row. Again, as I talked about when we were introducing this earlier, we are benefited here, we're blessed here, I would say, by the fact that the change row is always in 1 to 1 to 1 ratio. So my change row is always going to have the same element all the way across. So some of my acetic acid dissociates, sorry, I couldn't come up with a word, dissociates, and we're going to get equivalent amounts of hydronium and of the conjugate base. Now we're going to do our column math. So 0.85 minus x is 0.85 minus x, 0 plus x is x, 0 plus x is x. So we have our three equilibrium values. At this point, we could simply plug this into Ka and solve the resulting quadratic equation. However, let's note that the Ka for acetic acid is very small, very much less than 1. So we can assume that this is approximately just 0.85. Our assumption is that the equilibrium concentration of the acid is essentially the initial concentration of the acid. Had a typo there. See, that's an equal sign. Our assumption is, again, that the amount at equilibrium is essentially what we started with. If we then take this approximate value and x, there's our new column math. We can then plug this into the equilibrium constant and solve for x. So again, my equilibrium constant is going to be hydronium times acetate divided by acetic acid, or very simply, hydronium times the conjugate base divided by the acid. Plugging our numbers in, that's x times x divided by 0.85, and that's 1.78 times 10 to the minus 5, because that's the given value for Ka. Or x squared divided by 0.85 is 1.78 times 10 to the minus 5th. X squared then multiply both sides by 0.85. X squared turns out to be 1.51 times 10 to the minus 5th. We take the square root of both sides, and we have that the hydronium ion concentration is 3.89 times 10 to the minus 3rd molar. We can now check our assumption that 0.85 minus x was essentially just 0.85. So the question is, does 0.85 minus 3.89 times 10 to the minus 3rd equal 0.85? Or does 0.846 equal to 0.85? Well, it's a difference of roughly, well, it's less than 0.4% difference. So yes, the assumption is valid. Let me show you this math now very generically, because it's going to give us a result that we can use and not have to do a Rice table every time. When we have a weak acid equilibrium, and we say, okay, great, here are my initial conditions. Initial concentration of the acid, essentially no hydronium and no conjugate base. Some of the acid dissociates, let's call it X. That produces an equivalent amount of hydronium and the conjugate base. So this becomes, doing our column math, acid minus X, and we'll just call that acid. 0 plus X is X. That's my equilibrium concentration of hydronium, and 0 plus X is X there. So generically, this becomes X times X divided by acid minus X, which is roughly equivalent to, or is approximately equal to, pardon me, hydronium times hydronium over acid, or very simply, hydronium squared divided by acid. We solve this for hydronium, and we get this result, that the hydronium concentration is equal to the square root of the Ka times the initial acid concentration. So let's note this very important result. I can then, given the concentration of the acid, I can then solve immediately without doing a rice table. I can solve immediately for the approximate concentration of hydronium. And then if I take the negative logarithm of that, I have the pH. Please note that this equation is going to be good as long as the acid concentration is at least 1,000 times the value of Ka. So the smaller Ka gets, the better this approximation becomes. The larger my acid concentration, the better this approximation becomes. Similarly, for weak bases will undergo this equilibrium with water. Remember, bases accept a proton. So going from here to here, we've picked up a proton to go from B to its conjugate acid Hb+. And water has lost a proton as it goes from water to hydroxide. Again, we can establish an equilibrium constant here, and we call it Kb. B is for base. That's going to be hydroxide times the conjugate acid concentration divided by the base concentration. And again, for weak bases, these equilibrium constants are going to be less than 1. In most cases, very much less than 1. And so there's only a slight or partial dissociation. Again, the bigger the Kb is, the stronger the base. These Kb's are usually markedly less than 10 to the minus 4th. And we find that weak bases fall into two categories. One of those is ammonia and the amines. The amines are compounds that are related to ammonia that contain a nitrogen with a lone pair to accept a proton. Examples of these would be things like methylamine or diethylamine. Virtually anything where we've got a nitrogen that's making 3 bonds, it's going to have a lone pair, so it fills as octet. This is an amine. The other class of weak bases are the conjugate bases of the weak acids. So F-, which is conjugate to HF, or Cn-, which is conjugate to HCN, etc. All of these would be weak bases. Our calculation approach is going to be just the same as it was for the weak acids. Construct a rice table, solve the equilibrium problem. So here's an example. Let's calculate the pH of a solution that's initially 0.85 in ammonia with the information, the given that Kb is 1.8 times 10 to the minus 5th for ammonia. So here's my rice table. Generically, base plus water gives me hydroxide plus conjugate acid. Specifically, ammonia plus water gives me hydroxide plus the ammonium ion. Again, this is the ammonium ion. We put our initial values in. Ammonia is 0.85. Hydroxide is essentially 0. Ammonium is essentially 0. Check my note out here on the side again. Our change row, once more, it's in 1 to 1 to 1 ratio. So minus x here, plus x here, plus x here. We do the column math. This is 0.85 minus x, this is x, and this is x. Again, we're going to assume that this is essentially just 0.85, that our final concentration of base is essentially just equal, our final concentration of base here is essentially just equal to our initial concentration because the equilibrium constant is very, very small. This means very little reaction occurs. Making that assumption, here's our new equilibrium values. We plug that into the Kb expression, and we can solve for x, which is our equilibrium concentration of hydroxide. So again, solving for X eventually gets us here that the hydroxide concentration is 3.91 times 10 to the minus third. Now notice we don't have hydronium this time, we have hydroxide because we're in the base domain. So rather than going directly to pH, we're going to have to go through pOH. pOH, again recall, is defined as the negative logarithm of the hydroxide concentration. We plug that value in from X, and we get pOH is 2.408. pH then is going to be 14 minus pOH. We developed this equation in the last video. pH plus pOH is equal to 14 at 25 degrees Celsius. And if we're not given a temperature, we're going to assume that that is our temperature. So the pH then is 14 minus 2.408, where the pH is 11.592. Notice that's markedly greater than 7, and that's good because since we have a Kb and we're dealing with the base equilibrium, we assume this solution is basic. The pH we calculate bears that out. Again, let's check our assumption. Is this assumption true? Yes. 0.85 minus 0.00391 is 0.846, and that is indeed approximately 0.850. So our assumption is valid. Doing similar math as we did for weak acids, for weak bases, we can develop a similar equation to calculate, in this case, hydroxide concentration if we know the base concentration and the Kb. And again, this equation is going to be good as long as the base concentration is at least 1,000 times the Kb. So again, note, if I know my initial concentration and I know Kb, I can get an approximate value for hydroxide. When I have hydroxide concentration, I can calculate pOH, and from pOH I can get to pH. Now notice that we could also work this backwards. So suppose I have a pH meter, I know I have a solution of ammonia, I want to know how concentrated is it. I can take pH, subtract it from 14 to get pOH. My hydroxide concentration is going to be 10 to the minus pOH. That means I'm going to know this concentration, OH minus, and then using this equation, I can calculate what the base concentration is. Notice if I solve this equation, I'm going to get that this is the OH concentration squared divided by the base concentration. So again, pardon me, I've said that backwards. My base concentration is going to be the hydroxide concentration divided by Kb. Again, square both sides of that, you get OH squared is equal to Kb times base. Divide both sides by Kb, and you get this relationship. The last thing we want to talk about when we're considering weak acids and weak bases is the relationship between Ka and Kb for conjugate species. So for a pair of species that differ only by the H+. Here's my acid dissociation. Ha plus water gives me hydronium plus A minus. Now, this is my conjugate base. This is my acid. Here is a base hydrolysis for the conjugate base. Again, there is my base, and here is my conjugate acid. Here are my equilibrium constants. There's the Ka for Ha, there's the Kb for A minus. If I add these two reactions together, the HAs cancel, the A minuses cancel, and I end up with what is just the autoionization of water. This equilibrium constant is Kw. So what we conclude from here is this important result. For a conjugate pair, Ka times Kb is equal to Kw. And then we would find that pKa plus pKb, again, pKa plus pKb is going to be pKw, which is 14. Again, here I've said there's pKa is this, that, and pKw is the minus logarithm of Kw. So if I know the Ka for a weak acid, then I can automatically know the Kb for the conjugate base. Here's an example. The Ka for HF given is 6.6 times 10 to the minus 4th. And so the Kb for F minus is just going to be Kw divided by Ka, or 1.5 times 10 to the minus 11th. Now let's notice Ka is a weak acid. It has a Ka of less than, of the order of 10 to the minus 4th, and Kf is a weak base. Its Kb is 10 to the minus 11th. Now, one last topic in acid-base equilibria. There's a third definition for acids and bases, and that was put forth by G.N. Lewis. Yes, that's our friend from Lewis Acid Structures. And because he's concerned with electrons, he chose to define acids and bases in terms of electron pairs. And so Lewis is going to define a Lewis acid as an electron pair acceptor, something that can accept a pair of electrons to make a bond. A Lewis base is going to be an electron pair donor. Now, it is important for us to note, under this definition, any Bronsted-Lowry base is a Lewis base. Lewis acids are going to contain at least one atom with an incomplete octet, or we would say they are electron deficient. Here's an example. Here is borane. You may or may not recall BH3, but that's borane. Notice the boron is electron deficient. It only has 6 electrons around it. Here is a Lewis base, ammonia. And what happens here is this pair of electrons goes from being a lone pair on nitrogen to making this bond. Again, there's my curved arrow. My electrons are going from the nitrogen. So the nitrogen is donating an electron pair. The boron is accepting the electron pair. And we have this Lewis acid-base salt. This concludes our discussion of acid-base equilibria. Our next video will be a short video talking about buffer systems.